Okay. Well, we got 4 people here. two real, 2 virtual. Is just me or does the AC feel like it's off?
Good for me. Cold.
Okay. Just my heart's the only thing that's cold. Everything else I tend to be warm.
Really? All these years?
Sorry, I'm thirsty. Need a drink. So today's a review day. I'm gonna do a problem session and kind of go over the homework that that students had the hardest time with. So and let's start off here. So this is actually the one that students had the worst time with. So according to the quantum mechanical model for the hydrogen atom, which of the following electron transitions would produce light with a longer wavelength? 3p to 2s or 4p to 2s. So if you remember the formula, the energy level of a specific level, quantum level, is the Rydberg constant. Well, it's negative Rydberg constant, 1 over n squared. And then the delta is final minus initial squared. So the bigger, so if this is a big number, this is going to mean higher energy. And so for the hydrogen atom, you have n equals 1, and it's going to be just the Rydberg constant. The n equals 2. So actually, let me see, try and draw the scale. The n equals 2 number is going to be here, and this is going to be infinity or free electron. So because n equals 2 is going to be 1/4. So 1 over n squared. And the next one, n equals 3, is going to be 1/9. N equals 4 is going to be 1/16. So you can see that already with this trend, as you go up higher, so this is going to be 1, this is 1/4, 1/9, 1/16, right? So as you get closer up towards the free electron or n equals infinity, the energy level spacings get smaller and closer together. So for having, in this case here, so for 3p to 2s, it's going to be this transition, and 4p to 2s, it's that transition, it's the yellow transition. So the longer wavelength, also, if you remember, the lambda nu equals c, or the wavelength times the frequency of the speed of light. Also, energy equals h nu, h is a constant, equals hc over lambda. Oops, lambda's c. So long lambda implies low energy. So the one with the longer wavelength is lower energy one, and it's this transition. So it's that one right there. It's the 3 to 2. So, but I'm going to go ahead and cheat and just, rather than go over each one, where's my cursor? There we go. Here's on one screen, and here it is on the other.
Does it matter if you use the negative constant if you did the same value?
Oh, was it? Did I have to go? How do I get on the other screen? Oh, there we go. The negative just means negative potential energy. So, okay. So, I know I'm just kind of telling you the answer, but I'm also trying to explain it as well, but it's going to be hard to go back and forth in this. So according to the quantum mechanical model, as a quantum number increases, the energy increases and the spacing between the energy levels decreases. And so That's kind of a weird way of saying increases, because it means that the potential energy becomes less negative. That's what I mean by increases. The potential energy becomes less negative. So the greater negative potential energy means the more bound the electron is, the less energy it has. And I guess we had a conversation offline. We were talking, I was talking to a nameless student. We were talking about waving in class. The student was asking about electron mass, and I said, well, it's a bad way to look at it, but electrons, a lot of times we don't even think of electrons and even protons in terms of mass. A lot of times it's a bad habit. We look at it in terms of energy, because by the term E equals mc squared. So I'm sure you've heard of E equals mc squared. So that means matter and energy are interchangeable. What happens when an electron becomes bound to an atom? It becomes less massive. So the amount of matter that an electron actually has goes down as it's bound to an atom. So also with that, if it gets annihilated like by a positron, it then well, unless the electron is promoted, it's going to be, the energy is going to be different coming off from it. But anyways, so the energy increases and the spacing between the energy levels decreases. I told you it goes from, so down here 1 to then n equals 2 is 1/4, n equals 3 1/9, 1/16, then 5 is 1/25, and then 6 is 1/36. So you get really closer to an asymptote. So there's an asymptote there at the top. So therefore the transition, the 4 to 2, would have bigger energy difference than the transition 3 to 2. So lower energy means longer wavelengths, and then the lower energy one would have the longer wavelength. So does that make sense? So feel free to jump in and talk anytime. You guys, I think I'm gonna turn my volume. Oh, volume is up. Okay. So I can hear you guys as you're talking. So the next one here, energy of 1.8 mole of photons at 1600.
The 8.67 PDF thing's kind of in the way of the notes, I think.
I'm sorry, what? Oh, you're right. There you go.
Thanks.
Thanks for catching that. I'm so involved in chemistry, I forget to communicate. So 1.8 moles of photons at 1600 nanometers. So the energy of a photon is equal to E, or I already had E, is going to be H nu, which is Hc over lambda, already before mentioned. And then all we got to do is then take the photons, the energy of the photon, and then multiply it by 1.8, then by Avogadro's number, 6.02 times 10 to the 23rd. So put in the numbers, 6.626 times 10 to the minus 34 joule times second. Speed of light, 3 times 10 to the 8th meters per second. Wavelength is 1600 times 10 to the minus 9 meters. And so you can see dimensionality, seconds cancel, meters cancel, and wealth of joules. So you then take that number, like I said before, multiply it by 1.8 moles, multiply it by Avogadro's number to give the number of photons. And if you do that, number 8.45. If you do that, then you get 1.35 times 10 to the 5 joules equals 135 kilojoules. So recap with this one. So if you have 1.8 moles of photons at a specific wavelength, you have a number of moles of photons, specific wavelength. you got to calculate the energy of the photon, and that equals Planck's constant h times the frequency. The frequency also, so wavelength times the frequency is the speed, and which implies then that the frequency is the speed divided by the wavelength. And so you can then speed of light, so speed of light, so Planck's constant times the speed of light divided by the wavelength. And then that gives you the energy per photon. Then you multiply it by the number of photons, which in this case is 1.8 times Avogadro's number. And then you get 135 kilojoules. Questions with this one? Brianna, am I going too fast? Okay, I see you ready. You're just enjoying the show, huh?
Me?
Yeah. So next problem. So what is the de Broglie wavelength when the velocity of an electron is 1.25 times 10 to the 5th meters per second? And we're also, we're discounting, I mentioned a little bit about the mass of electron changing. We don't really, it's very, very slight for a bound atom. So we really, it's not that going to be, even then it's not very significant. But mass of an electron, well, a free electron is 9.11 times 10 to the minus 31 kilograms. So this is one of those, like, if you want to, for this test, you might make a crib sheet. And one of the things you put in there is the mass of electron. I actually have the mass of electron memorized, as do Planck's constant. But I mean, then again, you know, I've been doing this for so long.
Did you ever get a tattoo like you?
I've never gotten a tattoo, and I wouldn't do that. I wouldn't pick that as my tattoo, I don't think.
I would. Well, maybe no.
Various constants.
This problem is the only thing that kind of like troubled me, just because I was thinking about things can't go to speed of light because it has mass. Like it has.
It's not going the speed of light.
Yeah.
Speed of light. So speed of light is 3 times 10 to the 8 meters per second. So that's about whatever. That's less than 2,000. So it's got another 2,000 times more or so speed to get to the speed of light. So it's 1/2000th the speed of light.
Right.
So it's not even enough. This isn't even fast enough to start seeing relativity. So at least not, you know, like, how do I put it? It would work for time relativity, but not for mass relativity. So like, it's above and beyond this class, but as your speed approaches speed of light, the momentum of the particle increases, or the apparent momentum. So it's another way, and of course, momentum is mass times velocity. So if the velocity is not really going fast in the speed of light, then the apparent mass of the object gets more massive. And so it just kind of works by the E equals mc squared kind of thing, where if you keep on plugging more and more energy and speed of light is not changing, that means the mass is going to increase. And so you can get in some of the particle accelerators, the electrons have the same mass of like a sodium atom. I remember reading about that. So, but anyways, that's when you get to like 99.999997 times speed of light. You know, that's just for really, really fast electrons. So you don't have to worry about this. That's on this. The relativity discussion is not on the test. I was just going off of an earlier email from a student. So unnamed student. So de Broglie wavelength, though, is Planck's constant divided by the mass times the velocity. So that means the de Broglie wavelength is then the Planck's constant, 6.626 times 10 to the minus 34 joule second, divided by mass 9.11 times 10 minus 31 kilograms. speed 1.25 times 10 to the fifth meter per second. And then you plug all that in. So let's just 851. Oops, I dropped my Apple Pencil. 851. It's going to be 5.82 times 10 to the minus 6 meters, or 5.82 micrometers. So, oh no, it's I'm sorry, nano. It's nano. Whoops, too small. Minus 9. I was like, that's a little big, actually. So that's this answer. I'm looking at the thing.
Like green.
You like the green? I like blue.
Green and blue. So this is off topic, but if I were to go the speed of light, I would just turn the energy.
No, you would just get more massive.
I get more mass.
Yeah, even more so than Thanksgiving coming up.
Wow.
Wasn't expecting that.
No, I thought that the faster you go, or the closer you get to speed of light, the more you turn energy. Because mass can't go to speed of light.
No, but you just your momentum increases. So I mean, it gets harder and harder to push you faster, and then it'll approach infinity. Your momentum will approach infinity as you approach the speed of light. So it's one of the limit arguments. But I have to also say it's speed of light in a vacuum. You can like diamonds, for instance, you actually can have electrons travel faster than light in a diamond and other things that have high index of refraction. So you will have matter traveling faster than light in materials that have a high index refraction, but you will not, in a vacuum, you will never be able to get matter faster than the speed of light in a vacuum. I'm surprised you didn't ask about quantum coupling, because that's instantaneous.
Electrons? Or
Yeah.
electrons?
Or anything that's quantum coupled. Because you're asking me all those quantum mechanics questions.
Yeah.
Yeah. I always thought that would be cool for like communication. I was wondering if they're going to be quantumly coupled spy satellites, because there's no way you could ever hack that. Not even Doctor Who could hack that.
Before to quantum, it would have to be the temperature of the components.
No, not necessarily.
No.
No, you wouldn't. You just have to have two things coupled. So
I've always thought about just teleporting.
they've done research on that. They can only make small things teleport. So, but again, this is above and beyond the class. So it's all the nerdy stuff. But I encourage you to study more science, because that's the fun stuff. But I mean, I know I'm a chemist, but a lot of this stuff, like living reagent problems, it's important, but it's not like, it's not like someone going to dedicate your life to studying, balancing chemical equations. The quantum stuff is more fun. So I guess I'm kind of encouraging those discussions. So anyways, anybody have any questions? Okay, a recap for this one. The Broglie wavelength is Planck's constant over mass times velocity. So Planck's constant is a constant, 6.626 times 10 to the minus 34 joules times seconds. Mass of electron is 9.11 times 10 to the minus 31 kilograms. And then the velocity is given. Did you want me to do I can do the dimensional analysis if you want. So a joule, a joule is a Newton meter, which a Newton is a kilogram meter per second squared. So a joule is a kilogram meter squared over second squared. So actually, I guess I think I mentioned this more. I don't memorize a lot of things. I just kind of remember where it comes from. So that means we have a kilogram meter squared per second squared times a second. all over a kilogram meter per second. And then we'll look to see what cancels. One of these seconds cancel, inverse seconds cancel, kilograms cancel, meters cancel, and then we're left with meters. So if you wonder where the units all come from. So any other questions or comments? Random questions, blurting of emotions.
I love you.
Whoa, that was unexpected. So, all right. So the carbon-carbon bond takes 348 kilojoules per mole to break. What is the maximum wavelength that you can use to break that bond? So yeah, convert 348 kilojoules per mole into energy to photon. So that means, let's see here. So energy per photon is going to be hc over lambda, which implies then that your wavelength is going to be hc over E. And you plug it all in. And so 6.626 times 10 to the minus 34, 3 times 78 meters per second, I'm sorry, joules seconds. Energy, 348 times 10 to the third joules divided by 6.02 times 10 to the 23rd. Because you have per mole. So the energy per photon, I guess I didn't go finish this way. It's going to be 348 times 10 to the third joules divided by Avogadro's number. Because this will then, that's a 3. So this energy per photon here, that's the amount of energy that one photon. So if this is 348 kilojoules per mole, you divide that energy by a mole to figure out the energy per photon, and then you have energy per photon is hc over lambda. We've had it before. Solve for wavelength, and then you plug in the numbers. Ooh, we lost somebody. And if you do all this, you will get, what is the answer? It'll be 3.44 times 10 to the minus 11 meters, or 344 nanometers, which is ultraviolet light. So, all right, so recap of this one, it takes 348 kilojoules per mole to break the carbon-carbon single bond. On average, what is the longest wavelength that you can do to break this bond? Well, you can look at the energy to photon is hc over lambda. You solve for the wavelength. Hc over E is the wavelength. And the energy per photon is the 348 kilojoules divided by Avogadro's number. So that tells you the individual energy of each photon. You divide that and you get 344 nanometers. Questions of how to do this one? Nope. Andre, you look like you're thinking.
Well, I was wondering why the first energy of the photon doesn't include the speed of light. So you have the kilojoules divided by Avogadro's number. Oh, because you're trying to get one photon. Okay, gotcha.
Yeah. Yeah, this is a mole. This is per mole, and this is the individual photon.
Yeah.
So. Anyone, any Zoomers, any questions? Nope, nope, okay.
Let's define the max.
Yeah, because you can go below that. So that's the lambda max. And so remember, so if you have, so here's the, well, so when you have a shorter wavelength, this means high energy. So a longer wavelength is low energy. So to break the bond, if you put in more energy, so let's say if you have a shorter wavelength, so instead of you have a 340 nanometer photon, it'll break the bond. A shorter one, 300 nanometers will also break the bond, but a 345 nanometer photon will not break the bond. So shorter ones can. Because remember, for electromagnetic radiation, when the wavelength goes up, the energy goes down. So high wavelength means low energy, and also low wavelength means high energy. So they're inversely proportional. And the minimum amount of wavelength you need there, or just the maximum amount of wavelength, the minimum amount of energy would be 344 nanometers, thereabouts. Does that make sense?
That is so weird. But yes, it does.
It's not weird, it's science. What do you mean it's weird? So, right, if you were in an ocean and there is one wave and then here is another wave front, which one's going to hit you harder? Right, the choppier one. Right, long wavelength. This is that's an easy day on the ocean. That's a rough day on the ocean. Makes perfect sense.
It makes sense. It's just weird to think about.
Yeah.
Those are good visual representation, but I don't know what it is.
Okay. So you're stuck with me in the meantime.
Yeah.
Rihanna, I'm sorry, did you have a question?
No, I just wanted to make sure I'm correct in my thinking. So, you say it takes 348 kilojoules per mole, would that be like, it takes at least that much? And with
Yeah.
more, it'll also break the bond.
Yeah. Yeah. Let's say my water bottle here. You want to separate me from my water bottle. My minimum amount of money that I will separate with is $20. Okay. If you offer me $15, you give me $25. Oh, right. So, but instead of dollars, let's have energy, right? So it takes a minimum of 348 kilojoules per mole to break the carbon single bond. So if you hit carbon with 400 kilojoules per mole, yeah, it's broken. If you hit carbon with 340, it's not going to break. Make sense?
So if you take 350 kilojoules divided by the mole, will you get a higher wavelength? Or
You will get a shorter wavelength. So 350 is higher energy, which means the wavelength goes down.
So it'll basically, it takes a minimum of 340 kilojoules per mole, which corresponds to a maximum wavelength of.
Yes. Yeah. Then I make that clear. We're looking for the energy of the photon. So the 348 kilojoules per mole, that is the energy of the photon. And so it's just the energy, and this is, since you have kilojoules per mole, so you have kilojoules 348 per mole, then if you divide that out, I can just, if you're wondering, I was trying to avoid doing calculations. We turn everything to a song. So 348 divided by 6.3. So, all right, this is going to be 5.78 times 10 minus 19 joules. So that is the energy. This is the energy of the photon's energy has to be 5.78 times 10 to the minus 19 joules. And so you take that number and you put it in that equation. And HC over that energy gives you 344 nanometers. Is that making more sense? I'm feeling like there's a little confusion here, and my teaching instincts say I need to talk more. Is there a specific question, or do you want me to talk more about something? Do you need more information and or illumination at for any topic?
I mean, I get it.
You're doing good? Okay. All right.
I just think, shorter wavelength, higher energy breaks the bond.
Yes. That is correct. Okay. So the next problem, 8.69. Although I'm surprised that a lot of people did really. So the class got this this course 100% got it right. Yeah. Well, the 8 students had tried. So I got 100% right. Although I know that the class has got, well, it used to have 24, it's like 22, 21 students in it now. But this one's a particularly hard problem. So I thought I would talk about it. So at least I think it's hard. I think it's the hardest, as far as the math is concerned. So there's 2 ways you can do this. You can use this equation, where the Rydberg constant is 1.097 times 10 to the minus 7 inverse meters. And you can solve all of that. So I'll just do it this way. 1 over wavelength is 1.097 times 10 minus 7 inverse meters. So final 1 over 1 squared minus 1 over 2 squared. So this, of course, equals 3/4, right? So because 1 over 1 squared is 1, 1 over 2 squared is 1/4. So 1 minus 1/4 is 3/4. So that means that your wavelength is equal to, you just have to inverse this whole thing. 1 over 3/4 times 1.097 times 10 to the minus 7, 1 over meters. And if you do all that, you get 1.22 times 10 to the minus 7 meters. So that's one way you can do that. That's infrared. No, it's not. No, it's not. No, it's all right. It's not infrared. That's ultraviolet. Sorry. I'm being not heckled, but mirrored. The other way you can do this is solve for the Rydberg equation, energy for photon. So you get the, energy equals hc over lambda, which implies lambda equals hc over energy. And then you can do 6.626 times 10 to the minus 34 joule second times speed of light, meters per second, divided by, what is the Rydberg constant? I don't remember what it is. This is one constant I don't have memorized. It's like 10 to the minus 18 joules or something. Constant. That's 19. Okay. We do not have the Rydberg constant here.
Isn't that it? You used it in the last equation, or what's that? 4.097.
Oh, that's a different one. That's a different way of doing it.
A different way to see the concept.
Yeah. I'm looking in chapter 8. Okay. 2.18. 2.18 times 10 to the minus 18 joules times 3/4. So if you do, you can do it that way, and you will get the same answer. That's an ugly arrow. It's more like a flower than an arrow.
Oh,
Yeah.
it's not ugly.
So 2 ways to solve that one. But I know I only taught this way. Or not, I guess not that one. I've only taught this way, but I was just also going to show you another way to do that as well.
Most students do it that way. Or we talk.
I have no idea because I don't see it work.
Oh, we can't see.
How do I prefer to do it? I prefer this way. Just because, like I said, I kind of, that's actually a harder way, but in my mind, I just kind of conceptualize, I go thinking wise to the solution. This way is easier. That way is easier, and it's also in certain labs. I don't know. Did you guys do like a lab with Fisher on the hydrogen atom? Did you do a lab with you like that? Yeah, I know UH Manoa does a lab that way, and they use that equation.
It just for me it seems like we just to think about one of the.
Yeah, it's a little, yeah, because then you at the end you have to invert everything. So it's a faster way to the answer, but it just gives you the wavelength, but I mean, it works. And like I said, there's certain labs do that. Like UH Manoa, they have a lab on that.
Fisher said next semester he's going to be doing things with university.
Yeah, 162 is a tough class at Manoa, a lab at least.
So that first method just multiplies and divides the constants out already for you, basically.
Yeah. Yeah, but yeah, don't forget to invert it at the end.
Yeah.
Also, we can't sign up for 162 until we finish this class, right?
You can sign up for it now.
Oh, I tried and it says it. I don't need the prerequisite.
You have to email me and then I can override you. Yeah, so let me know if you have any other errors, but I'll forget. So email me. Never done that for some of your classmates, so I know how to do it. So, anyone have any other questions? Nope. Okay. So, actually, how did this class do? Let me look at I wanted to talk a little bit about quantum mechanics, quantum numbers. Oh, 100%. Oh, and this actually the pooling 18,147 students, 98.8% correct. So actually, I guess I don't have to go over this, but I wanted to kind of give a review. Right, so remember the quantum numbers, N, L, M sub L, and N can be 1, 2, 3 integer steps up to infinity. L is bound by 0, 1 up to n minus 1, and then M sub L is bound by minus L plus 1, 0 to L plus, or to, not L plus 1, to L, just integer steps, including 0. So for L equals 0, M sub L can only be 0. For L is 1, M sub L can be minus 1, 0, and 1. And L equals 2, M sub L can be minus 2, minus 1, 0, 1, and 2. Like so.
So N can never be zero,
No,
otherwise there's no atom.
there's no principle. Yes, well, I guess n can be 0 if there's nothing. You can have a null set of 0. 0, I guess it's a subspace. You have a subspace of 0.
Like an atom in a black hole.
That's just the linear algebra, kind of nonsensical thing. It wouldn't mean anything because it has nothing. Because n equals 0 would have no interaction with anything. It wouldn't have mass, and it wouldn't have any interaction with things that have mass or energy or electric fields or anything. So I wouldn't even take up space. That's oh well. Actually, I don't know. I guess it could take up space. That would be a theoretical particle. Of course, it doesn't mean anything. A particle that takes up space but has no interaction with anything
But it doesn't, right? It doesn't,
does not.
but it takes up space.
Yeah.
It would be gravity.
By the current theories, no.
So it's like the one thing I'm trying to figure out, right, is gravity.
Yeah, it seems like seeing if there's a wave particle duality with gravity. So we'll see. But again, above and beyond this class. Someone listening is like, what the heck is this guy teaching? All right, but I wanted to go over in terms of review. All right, so problem 9.66, orbital diagram for cadmium +2 and gold. So here is cadmium. So cadmium is going to have, this is the 1s, I guess you can, 1s, 2s, 2p, 3s, 3p, 4s, 3d, oops, 4p, 5s, 4d. So let me just write out cadmium's all the way at the end here, full shell. So till I got, oh, I guess, yeah, that's fine. So it's actually going to be cadmium is going to be like this. So I'm following Hund's rule, if you've noticed, in the Aufbau principle.
Isn't a 3D fill for
No, 4s will fill it first. And then, so here's cadmium. Now for cadmium +2, it's going to be the highest N. Oops, I misspelled highest. Highest N first. So the 5s is higher than 4d. So we move 2 electrons. It's going to be taken from this orbital here. So that's the orbital diagram. And then if you're going to write it out, so if you want to write out the cadmium +2, you can write it out as krypton, core, and just 5s 0. I'm just doing it for emphasis. You should not include that. 4d10. So that's cadmium +2. So, but you would not write that. You would, the way you would the way you would actually write it would be like this. Like that. So you would write cadmium +2 like that. question with that? And gold, I guess gold's down here. Gold's right here. So actually, I wouldn't ask this question because gold is a exception. So you can see this table here gives you the one there. Well, this is gold metal, and then the electron, the +1, the +1 would then, this would just become 0, and you would have xenon 5d10 for gold +1.
It was gold +2, then you're going to.
Yeah, gold +2. Well, gold doesn't really have a +2, it has a +3. So
Does that mean that it takes out the 5D? Or still takes out the S?
yeah, it takes out the S first. If you can read that, so. That would be gold +3. Goes to the S are taken off first.
And it's stable with 8 electrons and its 2 orbitals?
Gold ions are very reactive. So gold metal is very unreactive. Gold ions are extremely reactive.
Like,
So
copper. So
yeah, but even more so. So yeah, you can get you can buy gold ions to electroplate your own jewelry. That's not really electroplate, it just reacts and coats it. So let's say you wanted to make a golden penny or something like that, and you just take a penny or throw it into a gold +1 or a gold +3 solution, and it'll start forming gold over the metal.
does it react well with oxygen?
Gold nanoparticles react with oxygen. Gold bulk metal tends not to. Platinum actually surprisingly reacts with oxygen. A lot of time, like my platinum ring here that I'm wearing, the surface is going to have oxide on it, but the gold ring is not.
I mean, it's not like iron.
No, it's not going to tarnish. It's not going to react really at all. Platinum is just a very active metal. So you have a platinum surface and you're just going to have oxygens attached to the surface.
But then after that, the oxygen won't get through anymore.
No, it's not going to.
Someday.
Yeah, it'll draw like electron density away from the platinum, but it's not going to form like platinum. You're not going to form like a platinum oxide, salt or on a compound. You're just going to have oxygen disassociated on the surface of platinum. So no, platinum, sometimes I wonder about platinum rings because, I wonder why it doesn't burn you in a way, because hydrocarbons like oil, it's going to be reacting a little bit, I guess it's, yeah.
Well, it has an oxide layer.
Yeah, well, you can still get the hydrocarbons on there. There's probably also not enough activation energy. So I guess you do need a little bit of activation energy to go, even though it's at this temperature. You probably, you need to heat it up. I guess it's not too surprising. But platinum's just really reactive.
So, say you have it in water, and just do the same thing. Like, would it take that luster from the water molecules?
It might, then you have the water might break apart. I'm not sure about the water chemistry though. We more study platinum when it comes to hydrocarbons, because we use it like a catalytic converter, for instance, has platinum and or palladium in it. So platinum and palladium. I'm not so sure about water. Hydrogen will break apart.
Right.
I'm trying to think. I think it probably would. You probably would get hydrogens on the surface. But then you would start forming molecules like hydrogen gas and hydrogen peroxide. So I guess the answer is probably not appreciatively that much. Yeah. To be honest with you, I don't know. But you can throw platinum in water and it's not going to do anything. The other thing that water, I mean, of course, boils at 100 degrees Celsius, and that's not that hot. So, anyways, again, not in this class at all. So, science. Well, it's your bonus. It's your bonus for coming to class, is you get to have this extra stuff. So, funny enough, like if certain colleges, I know, like when I taught at Berkeley, like as a grad student, you could not teach from the book because then no one would show up to class. They'd have like talk about other stuff outside the book.
In that one, you learn more than what the book.
I mean, different learning techniques. No, not in the book. Oh. All right. So the next one is electron configuration of chloride. So here's chlorine right here. So, and then the electron configuration of chlorine is going to be, so Cl is going to be neon's configuration, 3s2, 3p5. So, right, 3s2, 3p1, 2, 3, 4, 5 for chlorine. And you have an extra one, so extra electron, so chloride is going to be neons 3s2, 3p6, which is the same as argon, of course, which is the same as argon's configuration. Yeah. So I think we have, a couple more. So element 4, should copy this. Erase. So argon 4s2, 3d10, 4p1, 2, 3, 4. This one is selenium. So this one is selenium. Argon 4s2, 3d1. So 4s2 to 3d1. It's going to be right here. So right, argon over here. 1, 2, 3d1. That's scantium. Or SC. SC on this one right here. The argon's 4s2, 3d1. So you guys seeing how I'm doing this?
Is that with a T or a D?
No,
That's what it was.
scandium. I can't spell for crap. Scantium, okay. All right. It doesn't say where it's from. Okay.
What was this German?
This is German word.
Right at the very top.
Oh, okay, German. Okay, well, I don't know if that's necessarily because like tungsten is wolfram. Do they?
Oh, yeah, that's also true.
Yeah. I don't know if they, because chemistry used to all be in, they always say it in German. Yeah. Like because in World War II or pre-World War II, Germany was the most technologically advanced country in the world. Now it's America.
Hail hydrogen.
What's that?
Hail hydrogen.
Yeah, hail hydrogen, yes. So, not even saying it right, man, it's Heil. That's so I mean, that's why it has German in there, because chemistry majors used to have to learn German. Kind of like nowadays, everyone has to learn English. Maybe one day we'll have to learn Chinese
After this hypersonic whistle test. Sure.
or Russian, I don't know. Well, we're on English now. Well, Germany is getting back up. Like the Pfizer vaccine, BNT, that's German. So Germany still does good science. So the next one, Krypton. I'll do different, I'll do pink. I think you get it. Krypton, 5s2, 4d10, 5p1. That's indium. So this is gonna be indium. And the next one is gonna be xenon, 6s2, and that's barium. So, but anybody have any questions on how to do these ones? So that one's indium and this is barium. You ever heard this lame joke? What do you do with a chemist who's passed on?
You bury him.
You bury him, yes. All right, last one. Which one would you expect to be a very reactive metal? And reactive metal would be, it's real easy to rip off the electron. It's going to be right here. Not surprisingly, this is going to be the alkali metals, right? And a reactive non-metal is going to be this one. Well, I'll circle that one, reactive metal, reactive non-metal. But this one, not surprisingly, it's a halogen. They can to form salts. So, but that was just one of the questions, but okay, I'll cover that. But
Theoretically, could we have an infinite table of elements?
no, because eventually the atom gets so big that it would turn into a black hole. Right, because you could argue that a neutron star is a nucleus. And if a neutron star gets big, well, black holes are neutron stars, but they become singularities. So eventually the atom would become a singularity.
So neutron stars are basically one giant atom,
Yeah,
but they're not big enough to collapse.
they're one huge nucleus.
Yeah. But then that itself would be an element, like a unique element, right?
You could argue that, yes. But practically speaking,
There's probably a pool of different elements.
yeah, the elements really after maybe, I mean, if you look at the last element that we probably use anything for is californium.
It's a funny symbol.
Because I mean the rest of them don't do anything. They're so unstable, they're so radioactive. Californium we use for as a neutron source, and it can be used like in nuclear weapons and or for a neutron source for spectroscopy. So you can see the half-life, if you can read that, it's 901 years. But I mean, when you start getting like niponium here, or nihonium. The half-life, they have half-life is 20 minutes.
Oh, and that's only on Earth. It's not like it's 20.
No, it'll be anywhere. So the super heavy elements, they don't have,
Like him.
they have half-life
Oh,
is
Ken's getting closer.
Oganesson, yeah, he's half-life of 5 minutes.
Poor guy.
I feel sorry for francium. I mean, here's francium. Here's a half-life is I have a half-life on here. 22 minutes. Like the element we named after France is not very usable at all. Of course, americium named after America. Our half-life is that's a pretty long half-life, 7,000 years. Use it to make smoke detectors. Don't really use americium that much for anything. Of course, polonium. Polonium is a radioactive element that's named after Poland. But you guys ever seen the movie Kate? I guess I asked you guys that. You've seen the movie Kate on Netflix? No. They have polonium in there.
What do you use it for?
Poisoning.
Oh, well,
Polonium, yeah. The Kremlin uses polonium to poison people. That's their poison of choice.
in World War II,
No, it's contemporary.
they still do it.
Yeah.
Is it factual or is it not? Is it fiction?
No, it's fact.
Oh, really?
Yeah, they killed a spy that defected in England using polonium. Yeah, you'll see it. It's weird. It's almost exclusively used by Russia.
Or just pull into it.
Well, no, it was just Marie Curie. She discovered it and she named it after Poland. You know, like it's like hometown pride. Here's the Curie. Where's curium? Here's curium. There's Marie Curie. And she won 2 Nobel Prizes.
What for being alive?
Nope. She and her daughter won one too. I mean, talk about an incredible person winning 2 Nobel Prizes, and then your family, and then your daughter earning one.
Was their daughter a chemist too?
Physicist, yeah.
Physicist?
So anyways, I'm out of things to talk about. So does anybody have any questions about anything? So, well, in that case, I will go ahead and stop recording and I will diligently sit here because if you guys want to ask questions, but yeah, if you do want to, if you